Good morning, ma'am. I'm Ragana Santosh. I'm from Adikavi Nanne University. During my internship at Emertxe Information Technologies, I worked on my EV ADAS embedded system project using STM32 Blue Pill. In this presentation, I'll explain the embedded concept, what I learned in EV, what I learned, and EV ADAS prototype I developed. The objective of this internship was to learn embedded system development for automotive applications. I gained hands-on experience with STM32, embedded C, HAL drivers, UART communication, timers, interrupts, and Python dashboard development. An electric vehicle runs using batteries instead of using fuel. ADAS stands for Advanced Driver Assistance System, which improves the vehicle safety using sensors. My project combines these two component concepts. Embedded fundamentals. Microcontroller is for the brain of the system. Real-time systems for responding with a fixed time. Firmware for software running inside the STM32. FSM for control the vehicle behavior and using different states. STM32 Bluepill architecture. STM32 Bluepill is the controller used in this project. It has GPIOs and ADC, URTA, timers, PWM, and interrupts. These peripherals are help to interface sensors and control the system. Sorry, uh, Cube ID, STM32 Cube ID for writing and debugging the code. HL drivers simplify the peripheral programming, and Tera Term monitor URTA output. VSPE create a virtual serial port, and Python dashboard for display the vehicle data. Hardware components used STM32 Bluepill, HC, SRO4, SRO4U ultrasonic sensor, temperature sensor, potentiometers, LEDs, push buttons, URTA. Uh, Coming to the EV ADAS architecture, the sensor sends the data to the STM32. The controller processes the inputs and using the FSM. Then the processed data is transmitted through RTA communication protocol to Python dashboard. If any unsafe condition occurs, warning LEDs and alerts are generated. Now coming to the FSM. FSM have five states: park, ready, driving, regenerative, fault. Now parked, vehicle off mode, ready, system on, driving for vehicle moving condition. Regenerative, braking while up, brake while applying, while charging the battery. Fault, safety for shutdown. Uh, this FSM makes to system organized and easy to maintain. Okay, coming to the sensor, HC SR047 sensor detects the obstacle distance. Temperature sensor monitor the motor temperature. Potentiometers simulate the battery SOC. SOC means state of charge. Embedded scheduling. A 100 millisecond timer interrupt execute periodically. Every interrupt perform three tasks: read sensor, execute the FSM, send the URTA telemetry. URTA communication. This STM32 sends the speed, temperature, battery, SOC, distance, and FSM state through the UART communication. Python dashboard receives and displays these information. Dashboard. The dashboard shows a live speed, SOC, temperature, distance, vehicle state, and graph. It's a monitor to monitor the vehicle in real time. Safety features: collision warning, automatic braking, battery protection, fault detection. These are the system have safety features. Software flow. After installation, the firmware continuously reads sensors, processes the data, updates the FSM, transmit telemetry, and refresh the dashboard. J- uh, During this internship development, I faced UART communication issues and timer configuration problems or sensor calibration and FSM transition bugs uh, and dashboard parsing issues. I solved them using debugging with Tera Term, UART logs, and ChatGPT, proper time calculations. Lo- in this internship, I learned Emertxe, STM32 programming, HL drivers, UART communication protocol, interrupts, Python, debugging real-time systems, and FSM design. Future enhancement for Canvas. These Canvas to replace the URTA communication protocol and line detection is a line detection means add a camera based LAN keeping assistance using image processing, cloud monitoring, stream telemetry to a cloud, dashboard for remote fleet monitoring, and OTA updates. Enable over the air firmware update the without any physical reflections. Internship outcomes and conclusion. Uh, this internship improved my embedded C programming and debugging the real-time system development skills. I also learned how to build a automotive embedded application from hardware to software. Technical knowledge. Again, also technical knowledge, practical implementation, debugging experiences, teamwork, industry exposure. Thanks for this valuable time. I'm happy to answer this, submit this PPT. Thank you. Now, coming to my STM30 IDE, I'll show my code. Uh, this is our EV dashboard. I'll open my okay code. ADAS.h, common.h, EV.h is there. EV.h, fault.h, common.h, these files, and ADAS.c, ADAS EV control C and fault C, main C, and pin configuration of this STM32. Okay, and and set up the VSPE virtual terminal, and this is CMD. Coming to hardware parts, the this is STM32 board. Here I am playing the my code, and these pair spots. Wait a minute. These pair spots are I'm using ultrasonic sensor for left, ultrasonic sensor for right and front. The potentiometers for acceleration pedal, brake pedal, SOC, temperature, and virtual terminal for and LEDs. Okay. I look at my virtual terminal, speed, SOC, torque, uh, rail upline, temperature. Okay. Uh, for the first ultrasonic sensor, trigger pin connected to the PB2 and PB3 for echo pin, and second one for trigger pin for PB4 and echo pin for PB5, and for front trigger pin for PB0 and PB1 for echo. And coming to the potentiometers, port 1 for acceleration pedal, PA not connected, and P2 port 2 PA1 connected. This is for uh, okay, brake pedal connected, and port 3 PA2 connected. This is for SOC state of charge, and PA3 connected to the temperature, motor temperature, and LEDs for collision warnings. PB8 connected to the red LED, PP9 connected to the blue LED, and PB10 connected to the green LED, and PB11 connected to the yellow LED, and as well as for virtual terminal, PA9 connected, and transmitter for PA10 connected, receiver for PA9, and baud rate coming to the its speed 115200. Okay, this is my Python dashboard. Okay, coming to the torque is minus 16, and acceleration 45%, brake is 29%, motor temperature is 34%, alarms non, fault non, signal is on. For this condition, I will change this. Just a minute. Uh, See this red LED is blinking because of ultrasonic sensor detects the vehicle. It means a vehicle. Uh, uh, Here critical warning alarm critical is critical. It's blinking. Front. Uh, Here I'm changing. Just a minute. Front ultrasonic sensor decreasing. Then here distance is decreased in between EV vehicle and another vehicle. And I'll change my another also, and these also. Okay, these vehicles are showing. Okay, and my speed 8 kmph. Now, as usually, reduce my. It's automatically off. Okay, see this, and my torque is then. I will change this acceleration and brake increasing temperature also. Here, uh, observe this change. Uh, Actually, firstly it minus 16, now 31. Acceleration 45, but now it's 65. And brake, firstly 25%, now it's changed after 56%. Motor temperature also changing, slowly increasing the speed. Uh, and, and this is my virtual terminal. Okay, this is my overall EV ADAS project. It's done. Thank you, ma'am. Thank you.